Hello, my name is Christopher OHARA, and today I'll be presenting space dust and the Lotus effect. So I'll go into the introduction and background, which is the use case of my research on this. 4 different methods, their results, some discussion, conclusion, and future perspective and recommendations. The image on the right shows a computational model of the Lotus effect, which we should all be familiar with. So space dust is a ubiquitous challenge because on the moon and other celestial bodies, we have this space dust that's everywhere. And because there's no environment or atmosphere to create things like rain, the dust stays in a dust form for a long time. Because of this, we have to look at the problem domain where, say we have a lunar habitat and we have an astronaut going into the field and a rover. They might go out to do some samples collection or some research. They get covered with this dust, and then they bring it back to the base. And then it gets everywhere inside the base. This is quite problematic. If we look just from the astronaut going out's perspective, when they bring it back inside, we have these valves that can get clogged, ports that get clogged, filters that get clogged, and we have finite filters. They're hard to clean. Electrical sockets, so we can have shorts, and turbines also get clogged. And now basically it's everywhere. This is not good. So it's also electrostatically sticky because of the solar winds in space. Basically the particles become charged, making brooms and brushes ineffective. One approach is to try to add water to the dust, but this basically makes it cake and it's not a good usage for water. And it's also toxic to humans. So in the lab results, they found that 1 scoop, which is about a handful, can kill 90% of lung and brain cells. On the image on the right, this shows the astronaut Cernan in Apollo 17. And we can see that on his spacesuit, we have space dust. It's also on the tool net. It's on the hatch. It's everywhere. And we already see that it's dangerous. Making it even more dangerous is it's sharp. Right? There's no erosion on the moon due to wind. So we have these particles over here. This is from an SEM scan, where they have these basically jagged edges, and these can slice lungs. So this image shows a porous material and the jagged type materials from the actual lunar space dust, as compared to what they look like on Earth. So these are little micrometeorites from space, and the space dust on Earth is quite round and smooth. The composition, it includes things like glass and ilmenite or olivine, and the sizes of these particles are between 2.5 microns and 90 microns, meaning they get stuck in all of the fibers of the spacesuit, and they can also do damage to the spacesuit, and this is, it's quite a hassle. So now that we've seen that there's a motivation and need to solve this challenge, we can look at the methods. As you might recall, we have the Lotus effect, which is a super hydrophobic method based on the multi-scale structures or the architectural structures of the Lotus plant. So here we can see a zoomed in features of a lotus leaf. We have some small papillae, right? And even smaller, we have these nano hairs that actually contribute to the self-cleaning properties of the lotus leaf. And this is because the water contact angle is around 160 with a small sliding angle. So when we add a liquid to these type of surfaces, they have a self-cleaning effect. NASA has something called a wet chemistry 2 implementation. I'm not going to go through all the details of this. You can always pause the video because it is quite interesting. But in general, there's a nanotexture substrate it gets cleaned with a low residue soap and distilled water and rinsed in acetone. They add this primer of an epoxy binder, typically. Air dry it for 20 minutes, bake it for 2 days, spray on a fog coat of silicate, and then let it sit. Then there's this self-assembly monolayer, which is applied, and it consists of endecane, which we should know from class, and a concentration of this perfluorooctyl trichlorosilane. And then they remove the substrate, rinse it, and bake it again for 30 minutes. It's a time-intensive process, but then we get a familiar architecture where we have this nanostructure, microstructure, and then a hierarchical structure. These substrates have these pillars, and eventually they start to look like little lotus flowers where we get the Lotus effect. This image on the right shows the process which was on the previous slide, where we have substrate, primer layer, and then this nanotexture layer with an epoxy binder, and then self-assembling monolayer. For another implementation, we have something called ultrafine powder coating, where they add it to these polymeric surfaces. It consists of a solution containing this polytetrafluoroethylene, or PTFE, which has a really ground up small size of 15 to 20 microns. They blend it into some hydrophobic nanosilica powder solution and electrostatically spray it onto a substrate and bake it. So voltage is applied to this spray gun and the powder is fed in. It's sprayed onto some substrate, baked, and we get a nice super hydrophobic coating. Another implementation is Lotus wax. So this is Koch et al.'s favorite approach. They have these basically these structures right here. These are bio-inspired from the Lotus wax, and they try to make a silicon version of them with these pillars. We have an array of pillars, and they're coated with this wax, and it's covered with a self-assembled alkane and then crystallized. And this can be applied to different artificial structures. Depending on the structure, it will have different behaviors. Finally, we have a paint by a brand called Stowe, and the paint is called Lotusan. Like regular paint, you add it onto a surface. They use some unique raw materials and binder combinations. They're not listed due to intellectual property, but basically a microstructure is composed of very fine mineral rock flour and metal oxides to give this zigzag or jagged effect. And as a droplet rolls down, it collects pollutants and it cleans the surface. The results from NASA, they took an untreated surface here and a coated surface with this WC2. They add some lunar JSC simulant to it, and then they try to clean it off. So they either brush it or tape it off, and we can see that the coated surface with the WC2 is it's nice and relatively clean, right? And this has a contact angle of about 150 from the paper from 10 years ago. For the UPC, the contact angle is greater than 160. We have some nice spherical water droplets, and both micro and nanostructures are formed similar to the lotus leaf itself, depending on the amount of the components that they add. So if they add a certain amount of different components, only nanostructures will form, or microstructures will form, and they'll be brittle. Finally, we have the Koch et al., or the Barthlott implementation, where we have these silicon pillars. And this is what it looks like zoomed in. And basically, it has a really high contact angle, but it suffers from being challenging to make, and also it doesn't work for all structures. We'll cover this in the discussion, and mechanical damage is bad. Finally, we have the Lotusan. It's been included for completeness, but they basically take two different samples here. One of them has been coated with the Lotusan, which comes out clean, and one of them has pollutants on it. And in general, there's a contact angle of approximately 140 degrees. So it's not quite super hydrophobic, but it's relatively super hydrophobic. Basically, these are the combined results. So from WC2, the research paper, it was approximately 150 degrees for the contact angle, but the patent in 2020, which is 10 years later, shows that the contact angle is, for the method I showed you earlier, is about 163. That's quite good. UPC is 160. The best one is the silicon structure plus the wax at 170. And then finally, the paint is 140. But we can't just say, oh, this is the best implementation because of certain limitations, which are in the discussion phase. So continuing to the discussion, it's not surprising that the WC2 from NASA is the most tested. They did some thermal testing, UV testing, and solar wind testing. They also did a light abrasion, so they have a 2-pound force cheesecloth that they pass on it 8 times. The contact angle drops from about 3 degrees over 8 passes, as compared to the UPC, where they rub some different cloth on it, wet cloth onto the material, and they have a change in water of about less than 10 degrees for the contact angle. But the UPC method, while it's effective, it's the materials being deposited with this thermal evaporation makes it kind of hard to mass produce. The Lotus wax, this was the silicon pillars, it has the most constraints. So even though it had the highest contact angle, you can't apply it to every material. The WC2 and UPC, you can basically spray on almost anything. This material, though, you have to grow those structures. And depending on if it's a non-polar surface, the platelets will grow in a vertical orientation. Polar surface, they'll grow in a horizontal orientation. And amorphous surface, only an amorphous wax will grow on this polar glass. It's also really easily damaged, as we can imagine. We have these little fibers that if you push them, they will break or bend. And the paint is a nice low-grade solution if you're going to paint your house or do something from home. It's not going to meet the requirements for space. Additionally, the research papers are limited on specifying regular maintenance. So how long do the coatings last? And the time to failure? I don't know. It's not said. And how do we reapply it with minimum effort? So can we just spray it on another layer, or do we need to polish it and sand it first? It's not covered, so this is something that needs to be discussed. And in conclusion, we are quite familiar that the Lotus effect is mature, but it has to be fine-tuned for the specific application. So for space applications, the WC2 method previously presented is the most mature and tested. But transitioning from research to production, like consumer level mass production, it takes time, 10 years for a patent. Additionally, there's no one size fits all. So things really need to be tuned for their use case. And then we have to test, and do our verification and validation. So our future perspective and recommendations, because we still have some more challenges, right? We talked about this mechanical damage. So synthetic textures, the solids, they get damaged and they lose their self-cleaning properties. Additionally, there's a little note for space, is that air trapped within a texture cannot stand up to pressure. So if you have low surface tension liquids, they can easily penetrate the texture, even with slight changes or increases in pressure. So you can imagine when they're out in the habitat, or they're out in the field on the moon, and they come back into the space habitat, there's going to be a large pressure change. So do we give a light shower? How do we clean it? It's not really clear. One consideration is to integrate a bionic approach from pitcher plants, which is called SLIPS, slippery liquid infused porous surfaces. Basically, there's a micro layer and a nano layer, and between these two layers is a lubricant that's been sandwiched and trapped in. And what might be nice is, and the way it works is if you put force down onto it and you damage it, it will, because this liquid layer is trapped, it will force the shape to be back the way it was supposed to. So maybe looking at the WC2 approach, on top of that bottom substrate, we could add a SLIPS layer. So if the little Lotus effect part at the top, the monolayer, gets pushed down, maybe this self-healing property can help push it back up. So thank you for your time. I look forward to your questions in the forum, and I hope you thought it was interesting.